Hi everyone, my name is Julian. I'm a graduate research assistant at the University of Colorado Boulder, and today I'm presenting some of the work we've done to investigate the effects of electric potential uncertainty on the relative motion control of the electrostatic tractor. So let's begin with a quick overview of the electrostatic tractor. Most active debris removal or EDR methods rely on some sort of physical contact, but this can be a disadvantage compared to some other contactless ADR methods. For example, if you try to capture a retired satellite with a net or a harpoon, then you might generate new debris fragments. And on the other hand, debris might rotate at rates with tens of degrees per second, which exceeds the capabilities of some grappling methods that utilize robotic arms, for example. So the electrostatic tractor has been proposed to relocate retired satellites from geostationary orbit without any physical contact. And the way this works is that you have a servicing satellite that emits an electron beam onto a retired satellite. Due to the emission of electrons, the servicing satellite will charge positively, while the debris charges negatively due to the accumulation of electrons. This results in an attractive force between the two spacecraft, which essentially acts like a virtual tether connecting the two spacecraft. And using its inertial thrusters, the servicing satellite can then tug the debris away and relocate it to a graveyard orbit. We use the multisphere method, or MSM, to approximate the forces between the two spacecraft. So the multisphere method represents complex spacecraft shapes using a number of spheres. And if you know the electric potential of the two spacecraft, you can invert the voltage to charge relation to obtain the charge on each sphere. And once you know the charge on each of the spheres, you can compute the electrostatic force and torque acting on the spacecraft. The relative motion control of the electrostatic tractor was developed by Hogan and Schaub. So the thruster acceleration that is required to maintain a certain separation or a certain relative position between the um, debris and the servicing satellite can be computed with the first equation on this slide. And it's a function, or it consists of a feedback term that tracks the relative velocity and position. And it also consists of a feed forward term that includes the electrostatic force that acts on the two spacecraft. If we choose diagonal gain matrices K and P, we can decouple the equations of motion and this makes it possible to analyze the behavior of the closed loop response. And we'll focus on the first of these equations, which describes the separation distance L between the two spacecraft. Now, we don't actually know the electrostatic force exactly. So if we misestimate the electrostatic force between the two spacecraft, the closed loop response will change as well due to the feed forward term. And if the force is misestimated, then the right-hand side of this equation is not zero anymore, as in the perfect estimation case, but the right-hand side is replaced by the difference between the actual force F and the estimated force. So the equilibria of the system are obtained using this equation, where the actual force F is a function of only the separation distance L if the electric potential of the two spacecraft are held constant. And if we assume that we have perfect knowledge of the electric potential of the servicing satellite, then the estimated force is a function of the separation distance L and the relative estimation error of the debris potential delta V. Now, to solve this equation, we need to choose a feedback gain KL according to a desired reference distance LR, which is the distance that we try to maintain, and according to an expected maximum estimation uncertainty delta V max. Once we've chosen the gain, we can solve this equation numerically, and we use the multisphere method to approximate the forces. So for a reference distance of 20 meters and a maximum uncertainty of delta V max equals 10%, we find these equilibrium positions represented by the blue line. So if the estimation error is negative, then the controller essentially overpredicts the electrostatic force, and as a result, the separation distance between the two spacecraft is greater than the reference distance, which is 20 meters in this case. So the servicing satellite will actually pull away from the debris, and and if the estimation error is positive, then the electrostatic force is essentially underpredicted, and consequently the servicing satellite will move closer to the debris. At some point, this equilibrium curve has a turning point, which is the critical point. If the estimation error exceeds this critical value, delta V star, then there is only one possible equilibrium solution that is negative. But in order to reach this negative equilibrium solution, the servicing satellite would have to move through the debris, which would cause a collision. So any estimation error greater than this critical estimation error must be avoided. And the area where these two spacecraft would collide is represented by this red area, the collision zone. So right now we've looked at one separation distance, 20 meters, or one reference distance that was equal to 20 meters. But what happens if we increase or decrease the separation at the reference distance? So it's worth noting that the feedback gain depends or was selected for a specific reference distance LR. So if we change the reference distance without actually updating the feedback gain, then the corresponding equilibrium will be a lot different than in the previous case. And that's what's shown in the left figure right here. So if we increase the reference distance, then the critical estimation error will increase as well. But if we decrease the reference distance from 20 meters to, let's say, 10 meters, then the critical estimation error decreases as well to just a few percent, meaning that even though we expected to have a stable closed loop response for estimation errors up to 10%, the two spacecraft might actually collide for a estimation error of just 5%. But if we update the feedback gain for every new reference distance, then the critical estimation error stays approximately constant at 10%. Now, so far we've looked at only one orientation of the debris, which is the orientation that is shown in this figure right here. But what happens if we actually change the orientation of the debris? How does this affect the closed loop response? So if we rotate the debris and bring it into different orientations, then we can see in this figure right here that the critical estimation error of delta V star is affected by that. The green areas show those orientations that increase the critical estimation error, which is good. But the blue regions show those orientations where the critical estimation error decreases, which would cause a collision for a small estimation error. And these blue regions, these dark blue regions here, here, and here, actually correspond to those orientations where some of the debris protruding structures, such as the solar panel, are directed towards the servicing satellite. And at the same time, this doesn't just those worst case orientations don't just decrease the critical estimation error, they also decrease the minimal separation distance between the servicing satellite and the debris. So at some points for the worst case orientations, the minimal distance between the two craft decreases to as low as just 2 meters, meaning that the closest point between the debris and the servicing satellite is just 2 meters apart, which is a quite drastic decrease when compared to a reference distance, which is 20 meters. So these two figures show how the effect of different debris orientations changes over distance. So on the left-hand side, we look at the attitude effects over distance without adjusting the feedback gain. In this case, the critical estimation error increases for both the worst case scenario or worst case orientation and the best case orientation. But if we update the feedback gain as seen on the right figure right here, then both the critical estimation error of the worst case orientation and of the best case orientation converge to our nominal 10% estimation error. So that shows that over distance, the attitude effects actually decrease, but they're still pretty significant, up to 50 meters, for example. So last, we compared different multisphere method models. In all the figures that I've shown so far, we've used a debris model that consists of 80 spheres and a servicer that consists of 108 spheres. But then we used also different MSM models with a smaller number of spheres, and also one configuration, the configuration F, which only consists of an effective two-sphere model. So on the right-hand side, we can see that only one of these models deviates strongly from the other ones. And this is the two-sphere model, the configuration F. But all the other ones are quite similar. And this figure shows how accurately the worst case orientation and best case orientation can be, how accurately these different models can calculate the critical estimation error for the best case orientation and worst case orientation. And interestingly, the error between configuration C and D is pretty much, it's the same error pretty much, even though the number of spheres was decreased by almost 40. But the reason for that is that between configuration C and D, we only decrease the number of spheres of the spacecraft bus. And the spacecraft bus does not have a huge effect on the attitude effects. So this shows that we can, if we focus the distribution of the spheres of the MSM models, if we focus the distribution on the structures like solar panels, then we can have a pretty high accuracy while still while using less computational effort. For example, for configuration D, we can decrease the computational effort by about 80%. So in conclusion, the critical potential estimation error decreases drastically for some orientations, and this also decreases the minimal distance between the service and the debris. But this can be avoided by choosing the feedback gain according to the worst case scenario. And we've also shown that lower fidelity multisphere models can also yield good results. Thank you very much for watching.